Hi there, welcome back. We have talked about straight wires and their magnetic field lines. We have discussed current coils, and now we're going to discuss a solenoid. A solenoid has some interesting properties that we will see in many applications. Think of a solenoid as a slinky. Okay, so now you have a coil, but a coil that has a length as well. So you stretch it out along the length and you have a current that is going through that coil. And this portion here is what is considered the solenoid. Let's take a closer look at this. So I'm going to draw once again the cross section, and the easiest way to draw this would be to show the little cross sections of wires on the top for each turn, a little cross section below for each turn. And so it's as if I took a solenoid and cut it, and you do have, like for example, this connected to this guy in the back, and then in the front it'll be connecting to this guy, and in the back it'll be connecting to this, and so on. Okay, so you see the way it's constructed. So in my example, let's say the current is going in this direction. So it goes behind the solenoid over here, comes out of the page, goes into the page, comes out of the page, goes into the page. So coming at the top, it's always coming out of the page. So I will have dots at the centers of all these circles at the top. And at the bottom, it's always going into the page. So I will have X's. So just like our discussion of the current loop, it's very similar. So I'm going to take a zoomed in view of just 2 or 3 segments over here so you can see more clearly what we're doing. So the current in the top loops is coming out of the slide, and in the bottom loops is going in. And using your first right-hand rule, which I hope you're getting a lot of practice by now, you can see that the current, when it goes into the loop, will create a clockwise magnetic field around it. And the current, when it's coming out in the top loops, it'll create a counterclockwise direction of magnetic field around it. I encourage you to pause the video and just use your first right-hand rule to confirm all that. Now you see some interesting things as we look at these directions. So in between the 2 wires, they are opposite each other from 2 adjacent coils, so they tend to cancel each other. Outside, they're all pointing to the left from the top wires, but from the bottom wires, they'll be pointing to the right, so they'll tend to negate each other a little bit. And then same thing holds good as we come to the bottom. They're all pointing to the left from the bottom wires, but from the top wires, they'll be pointing to the right, so they'll cancel each other. But the interesting thing that happens is in between or inside the solenoid. So inside the solenoid, you can see that all of these magnetic field lines are pointing to the right. It doesn't matter which coil I'm looking at, they're all pointing left to right in this case, based on the orientation of the current we took. So the end result of magnetic field in a solenoid ends up being that it is uniform inside the solenoid, meaning it's got the same magnitude and same direction everywhere inside the solenoid, and it's much stronger inside the solenoid than it is anywhere on the outside. So let's write down some of these properties. So the first thing is that it's uniform. The second thing is that it's pretty strong because of the additive effect of all of these coils. And then the direction is determined using first right-hand rule and the given direction of current. All right, having specified all this, we know how to figure out the direction of the magnetic field based on the direction of the current. We know that the magnetic field is uniform based on the contribution of all of these different coils. Let's see what the equation ends up being. The equation for the magnitude ends up being mu naught times N times I over L. L here is the length of the solenoid. So its units would be, in SI units, it'll be in meters. N is simply the number of turns. So in this example, I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 turns. At the bottom, when we zoomed in, I had 3 turns. A lot of industrial solenoids that we use for many applications, I'll talk about that in a second, typically would have thousands of turns because we want a strong magnetic field for a relatively small current. So I is the current and L is the length. So this will give you the magnitude of the magnetic field anywhere inside the solenoid. Of course, there will be edge effects here, similar to our discussion of parallel plate capacitors for electric fields. So if we ignore the edge and look at most of the solenoid, we will have a uniform magnetic field. So this is the strength or the magnitude of the magnetic field anywhere inside the solenoid, ignoring the edge effects. So as we are discussing this, you probably thought about the parallel plate capacitor, because the parallel plate capacitor between the plates of a capacitor had uniform electric field, and now we have uniform magnetic field. The parallel plate capacitor had a stronger electric field between the plates than outside, which is true here for magnetic fields. The direction for the parallel plate capacitor was determined based on which plate was positive, which plate was negative. In this case, it's determined based on the direction of the current. The magnitude of the electric field for the parallel plate capacitor depended on only three things. It depended on the charge separation between the plates, the material or the dielectric constant of the material between the plates, and the area of the plates. It did not, importantly, depend on the distance between the plates. And you see those similarities here also for the solenoid. The strength of the magnetic field depends on the strength of the current, the number of turns, the size of the solenoid, in this case just the length instead of the area, and then it does not importantly depend on the diameter or the radius of the solenoid, which will be the analogous element to the distance between the plates. All right, solenoids are used all around you. If you have magnetic swipe cards that unlock and lock doors, those are using solenoids and electromagnetic fields to open and lock those doors. All kinds of medical devices and all kinds of industrial devices use solenoids as valves to control the direction of flow, and also use them to lock and shut and open things. MRI machines are great examples of solenoids, and they're also used in kidney dialysis machines. All right, so this was a quick review of a very useful tool. We will be looking at more of this in the coming videos, but we covered the basics here. The magnetic field inside the solenoid is uniform. It is quite strong inside compared to the outside, and it depends on the current, the number of turns, and the length. It does not depend on the radius. Oh, by the way, the analogous element to the dielectric constant between the plates of a parallel plate capacitor would be a ferrous or magnetic material that fills this empty space within the solenoid, which boosts the strength of the magnetic field. We'll talk more about that later. But the important thing is that it does not depend on the radius, which will be analogous to the distance between the plates for a parallel plate capacitor. So we've talked about the similarities there, and then we've touched upon many of the applications of the solenoid. Thank you.